Hello, my name is Griffin Gonsman. I'm a freshman at the University of Colorado Boulder, and this spring I took a course called Cancer Drug Discovery through the MCDB department. Along with my fellow researchers, Leo and Vi, Professor Dr. Cheryl Pinzone, and Principal Investigator Eric Alfredode, we found that Acriflavine exhibits chemotherapeutic effects on our model organism, Drosophila melanogaster. Cancer at its core is uncontrolled cell replication. It is one of the most impactful diseases globally, with 50 to 100 million people currently living with it and a 1 in 5 lifetime risk of developing it. There will never be a single cure, but there is reason for optimism. The 5-year survival rate sits at around 70%, largely due to advances in chemotherapy. Still, continued research into novel drugs into the tumor microenvironment is essential. Our model organism was Drosophila melanogaster, the common fruit fly. We chose them for several reasons. Their life cycle is roughly 14 days, making them fast and cost-effective for running multiple trials in a short period. They also share approximately 70% of their genes with humans, and many human diseases have Drosophila homologs. Most importantly, during their larval stage, Drosophila cells are rapidly dividing, which mimics the behavior of tumor cells. This makes them an ideal model for testing a drug's chemotherapeutic capacity in toxicology and pathology research. Our drug of choice was Acriflavine, a synthetic molecule composed of tripflavine and proflavine, originally developed as an antiseptic during World War I and used to treat sleeping sickness. It has since been explored as a fluorescent probe in biological research and more recently as a potential chemotherapeutic. Acriflavine works with two primary mechanisms. First, it inhibits the dimerization of HIF1, a transcription factor that allows cells to adapt to hypoxic or low oxygen environments. Tumor cells rely on this adaptation to continue proliferating under immune system pressure, so blocking it disrupts their survival. Second, acriflavine intercalates into the sugar phosphate backbone of DNA, causing it to coil and kink, which interferes with replication. Together, these mechanisms make it a compelling candidate for oncological applications. Our hypothesis was that Drosophila larvae are treated with acriflavine. Their survival will decrease due to anti-tumor properties, specifically HIF1 inhibition and DNA intercalation, which would stop rapid cell proliferation and lead to larval death. For our methods, we began by creating a stock solution of acriflavine powder dissolved in DI water at a maximum concentration of 10 milligrams per milliliter. We then prepared fly food vials dosed with their stock solution, a negative control of DI water, and a positive control using colchicine, a known chemotherapeutic, also at 10 milligrams per milliliter. We also ran a dose response experiment using a 1 to 5 dilution series, producing concentrations of 2 10,000s, 4 10,000s, and 800,000 milligrams per milliliter. All vials had third instar larvae added to the drugged food and were run in triplicates. To collect data, we allowed the larvae to develop into pupae and counted alive versus dead pupae using a light box. We calculated percent survival for each vial and established chemotherapeutic and growth promoting thresholds based on 2 times standard deviation from the negative control. Any survival rate below the lower threshold was considered a chemotherapeutic hit. Looking at figure 4, our max dose experiment, colchicine produced a survival rate of 18%, stock acriflavine 61%, and DI water at 80%. A lower threshold of 76% was calculated, designating both acriflavine and colchicine as hits. In figure 5, our dose response experiment, colchicine had a 12% survival, stock acriflavine 45%, DI water 96%, and our 3 dilutions had a survival rates of 85, 54, and 56% respectively. A lower threshold of 95% was calculated, designating all experimental conditions and the positive control as chemotherapeutic hits. Analyzing the results, the max dose experiment showed statistical significance confirming acriflavine as a growth inhibiting factor. The dose response experiment also showed statistically significant hits across all dilutions. We identified a narrow chemotherapeutic window, meaning concentration matters considerably in determining survival outcomes. One unexpected result was that dilution 1 had a higher survival rate than the more dilute concentrations, despite being more concentrated. We attribute this to human error in counting and possible improper drug dosage rather than true biological effect. Overall, we conclude that acriflavine exhibits chemotherapeutic hits on Drosophila melanogaster at 10 milligrams per milliliter. Looking ahead, we would like to test a narrow dose range around 2 micromolar and 0.4 micromolar to pinpoint the exact threshold of efficacy and calculate the chemotherapeutic index of acriflavine on human cells to assess its real potential for oncological applications. I would like to thank Eric, Dr. Cheryl Pinzone, and our TAs, and the MCB department for this amazing opportunity. Thank you.